Hello, welcome to STEMists. Today we're talking about another theorem in number theories. Yes, another one. It's called Euler's Totient Theorem, and it is often used in combination with the Chinese remainder theorem. If you don't know what that is, check out our last video. As the name indicates, Euler's Totient Theorem is devised by Euler, who published a paper in 1736 proving the Fermat's Little theorem, which we will also cover later in the video. Then he proposed a generalization of Fermat's Little theorem, and that is our Euler's Totient Theorem. First, to understand the theorem, we must talk about what on earth is Euler's totient. The sign here is pronounced phi. If n is a positive integer, phi n is defined as the number of integers in the range 1, 2, 3, and all the way up to n that are relatively prime to n. For example, phi 6 is the number of integers in the range 1 to 6 that are co-prime to 6, which means 1 and 5, since 2, 3, 4, and 6 all share common factors with 6. So phi 6 is 2. Now you might notice, counting all the prime numbers from 1 to n might work for smaller numbers like 6 or 10. But what if it's 100, 1,000, or 1,000,000? Of course, it's impossible to count one by one. This is where Euler's totient function comes in. Let the prime factorization of n be p1 to the power of e1, p2 to the power of e2, and so on, till pm to the power of en. The function states that phi n, so the number of integers co-prime to n from 1 to n, is equal to n times 1 minus 1 over p1 times 1 minus 1 over p2, all the way up to 1 minus 1 over pn. So why is that? Let's still take the example of phi 6. The prime factorization of 6 is 2 times 3. Since the integers we want are relatively prime to 6, they can't contain the factor 2. And how often is the factor 2 present in continuous integers? Every two numbers. Half of the integers between 1 and 6 do not contain the factor 2. So 6 times 1 minus 1 half. We don't want the factor 3 either, and we know that it occurs every three numbers. In other words, they take up a third of the integers between 1 and 6. So what do? We subtract 1/3 of integers from this set, hence 6 times 1 minus 1 half times 1 minus 2/3. What do we get? 2. Exactly our answer from counting. Now you understand Euler's totient. We can talk about his totient theorem. The theorem states that if a is an integer and m is a positive integer relatively prime to a, then a to the power of phi m, remember that phi m is the number of integers between 1 and m that are co-prime to m, is congruent to 1 mod m. Let's look at an example. Let m equals 8 and a equals 5. 5 and 8 are co-prime. Phi 8 equals 8 times 1 minus a half, since the prime factorization of 8 is 2 to the power of 3. So phi 8 is 4. 8 to the power of 4 is congruent to 1 mod 8. So what's 5 to the power of 4? 625. 625 is equal to 78 times 8 plus 1, so congruent to 1 mod 8. It works. So how do we prove this theorem? You can pause the video and take a moment to think about it. A hint, you need to construct multiple sets regarding phi m and a, and use some multiplication and cancellation rules in modular arithmetic. You got it? Okay, here's the proof. We first construct a set called S that contains all the positive integers between 1 and m that are co-prime to m. Does that sound familiar? Yes, that's exactly the integers Euler's totient looks for. Let's name these integers x1, x2, and all the way up to x phi. Then we take all the numbers in this set and multiply them by a, and let's name the new set t. So t contains ax1, ax2, all the way up to ax phi. Let's look at some properties of these two sets. We know that all the numbers in set S are relatively prime to m by definition, and so is a. So when these two numbers multiply, their product is still co-prime to m, since none of them have any common factors with m. Now we will construct another set and call it t prime. We get the numbers in t prime by taking the elements in t and reducing them mod m. So it's ax1 mod m, ax2 mod m, and so on, up to ax phi mod m. Note that all the numbers in this set must also be relatively prime to m, since reducing a number that's co-prime to m mod m will result in a number co-prime to m. Another property of this set is that all the numbers are between 0 and m, not including m, since any numbers greater than or equal to m can be further reduced. Do you notice anything? The set sounds really similar to the original set S, right? Are they the same? Maybe they are. So to prove that they have the same elements, we need to prove that all the elements in t prime are distinct. Based on the multiplication rules of modular arithmetic, if x is congruent to y, then ax is congruent to ay. But as contrapositive, we can get that if x is not congruent to y, ax will not be congruent to ay. we know that all the elements in set S are distinct integers between 1 and m that are coprime to m, so none of them are congruent to each other mod m, which means all the elements in set T, ax1 to ax5, are also incongruent to each other. If they are incongruent, the numbers we get by reducing them mod m are not going to be congruent either, so all the elements in T prime are distinct. Also note that it is impossible for 0 to be in T prime, since 0 or multiples of m are not included in any previous sets. Hence, elements in T prime mean each and every single integer between 1 and m that's coprime to m, exactly the same as set S. Each number in set T prime can correspond to a distinct number in set S. Now it is pretty intuitive that every number in T prime will be congruent to a number in T mod m, since we get them by reducing numbers in T mod m. Since S has the same elements as T prime, each number in it will also be congruent to a number in T. Let's say xi1 is congruent to ax1, xi2 is congruent to ax2, and so on up to xi5 is congruent to ax5. What do we do next? We want to get a to the power phi m. We can get that by multiplying all the elements in S, then multiplying all the elements in T. So all the elements on the left from xi1 to xi5, and all the elements on the right from ax1 to ax5. Since they are all pairwise congruent to each other mod m, their products will also be congruent to each other according to the multiplication rule. This notation here means multiplying all the numbers. We can see that both products contain the product of all the elements in S, from x1 to x5, but the product on the right, the product of all the elements in T, also contains the product of all the A's. So how many A's are there? The number of A's equals the number of elements in set T, which equals the number of elements in set S. What's that number? Yes, that's exactly phi m, since set S is defined as all the integers coprime to m between 1 and m. So the product of x1 up to x5 equals a to the power of phi m times the product of x1 up to x5. We can cancel the product of all the x's from x1 to x5 since it is coprime to m and thus satisfy the condition for cancellation in modular arithmetic. Wow, here we go. The only thing left is a to the power phi m equals to 1 mod m. The theorem is proven. Now let's talk about Fermat's little theorem, the theorem Euler gets the generalization of the Totient theorem from. It's a special case of Euler's Totient theorem with certain restrictions on the conditions. It states that if a is an integer and p is a prime number and a is not divisible by p, then a to the power of p minus 1 is congruent to 1 mod p. Its proof is fairly simple. Feel free to pause the video and try to figure it out yourself. Yes, time to burn some brain cells. Got it? So the Euler's Totient theorem is applicable here because p is a prime number and a is not divisible by p, so it must be coprime to a. From the Euler's Totient theorem, we know that a to the power of phi p is congruent to 1 mod p. What's phi p again? The number of integers that are relatively prime to p between 1 and p. As a prime number, the only two factors p has are 1 and itself, so any numbers between 1 and p will be relatively prime to p except for itself. So phi p when p is prime equals p minus 1. A to the power of p minus 1 is exactly a to the power of phi p, and that is Euler's Totient theorem. Hence, we have proven Fermat's little theorem, which states that a to the power of p minus 1 is congruent to 1 mod p when p is a prime number and a is an integer non-divisible by p. Overwhelmed? No? Well, you'll definitely understand it better once you see some examples. Because of the time restriction, I'll make another video to talk about the application of Euler's Totient theorem and Fermat's little theorem in real questions. Stay tuned and subscribe!